Okay, so we have the pleasure to host here Professor Amnon Yariv from Caltech. Actually, we are celebrating, we are now in the period of celebrations. So last year we celebrated 50 years for the laser. In 1960, Theodor Neumann got the first ruby laser. And it's no surprise that we are now celebrating the 50 years for nonlinear optics, because I think these two events are related. A few months later, Peter Franken uses ruby lasers similar to what Theodor Neumann developed, and he sent it to a quartz crystal and got second harmonic. And I think this was the first experiment, or the first meaningful experiment, I think, in nonlinear optics. And also, so Professor Yariv, I think, is one of the founding members of both the lasers and the nonlinear optics areas. And I believe also in 1961 was one of the first papers by you, together with
Albert Feldman.
Yes,
on quantum nonlinear.
On quantum nonlinear optics, on actually on quantum treatment of parametric amplifiers. And we all know now that this process of parametric down conversion is the basics for quantum optics, and also for devices like optical parametric generators and optical parametric oscillators. So it's our pleasure to have here Professor Yariv, and we look forward to hear about the celebration of 50 years of nonlinear optics.
Well, glad to be here, and I'd like to thank my host, the physics department here in the EE Electrical Engineering Department and the Sackler Institute. And it's more or less an annual visit. And this year, when I thought about the topic, it said, can you hear me? All the way down? You cannot hear me?
Okay.
Okay.
Go for it.
All right. I gave a talk about a month ago in Hawaii. Okay, as you can see on nonlinear optics, and specifically, I spoke about the beginning of quantum nonlinear optics. So today I will more or less repeat the Hawaii talk, get some more mileage out of it, and try to tell you the story, some of the beginning of nonlinear optics, the main characters involved, some of the places that were involved, and my own work, which involved quantum nonlinear optics. And the quantum here is not just doing it quantum mechanically. It turns out that the quantum treatment leads to new predictions and new phenomena that were not predicted, cannot be predicted classically, which have become important more recently. Adia alluded to it. So with that, let's delve in. So I'll talk about some history, noise, coherence, it'll become clear, quantum formulation of nonlinear optics, prediction, observation of spontaneous parametric fluorescence, which is related to it, squeezing, and just mention some very recent work, not mine, but related at Caltech, kind of a new field which is being launched now, which is quantum interactions involving hypersound, ultrasound, and laser beams and optics. As Adi said, the field of nonlinear optics can really trace its beginning to one event. It's very seldom that that's possible. Usually something important happens, lots of people claim credit retroactively. Not so here. One day you picked up Fieser of Letters and you saw an article by Franken, Hill, Peterson, Weinreich on generation of optical harmonics. And what they did, shown here, that's from the original paper. They took a ruby laser. Mind you, the ruby laser was about a year old, demonstrated for the first time by Ted Mayman at Hughes Labs in Malibu, California. shone it on a quartz crystal, took the output, sent it through a spectrometer, a prism here, and observed, in addition to the main ruby light, most of the ruby light went through, there was a little spot here at half the wavelength, twice the frequency. So they have generated the second harmonic of the ruby light. As a matter of fact, the spot here was so small that the printer, the editor at Fizer Letters thought it was a smudge, lichluch, and erased it. So in the original paper, it wasn't there. Also, the conversion efficiency was 10 to the minus 9, give or take. So very low. So it didn't seem like a practical interest, but it signaled the first demonstration of a nonlinear effect. Maybe not the first, but that's the event that launched nonlinear optics, and that's why it's celebrated in 2011. That was a year after the laser. Here's the experiment. The ruby laser, etc. And here is a later experiment with a red beam entering a crystal. I think it may be with lithium niobate. And the second harmonic shown here is green, but actually a UV beam emerging from the crystal. Now I'll go back into the preoccupation with nonlinear effects antedates the 1961 event, goes back years before that. And the reason is microwave parametric amplifiers became a topic of interest, very active. And here's a fellow Mumford, which is very well known. Mumford is responsible for the concept of a noise figure of an amplifier, something you all use today. Essentially a communication engineer at Bell Labs. And here he says, the new generation of amplifiers based on variable capacitance diodes. A PN diode has a capacitance which depends on voltage. And if you apply voltage to it, you are actually modulating the capacitance. You vary it, so variable capacitance. And that can be, and I will show you how, the basis of amplifiers, microwave amplifiers. And he said to think about them, they have extremely long life because they're semiconductor devices, and they're probably very low noise. And either one of those will make them an important device. If you can combine the two, you have a very important device. So Mumford talked about that. But those are microwave devices, not optics. Probably, maybe one of the most important papers in the field, even today, is a paper that very few people know about. Have you heard about P.K. Chan? Have you? P.K. Chan was a scientist, again, at Bell Labs, communication department, and he talked about parametric amplification and frequency mixing in propagating circuits. In other words, imagine two transmission lines, classic transmission lines, each made up of RLC, coupled with capacitances, which are modulated by a third wave, which he called the pump. And he derived, and he showed that if one of them propagates a frequency omega 1, the other omega 2, the two neighboring adjacent transmission lines, and you send this intense pump wave, if the pump wave has a frequency equal to the sum of the frequencies which propagate the two transmission lines, here are the equations of the coupling, and you can amplify the two waves simultaneously. And what's more, he had shown, he had derived essentially what we all know today, that amplification involved generating one photon, although he didn't use that language, at each frequency simultaneously. And because he used traveling wave interaction, he also came up with the idea of phase, that you needed to phase match. You needed to essentially have a phase relationship between the three waves, pump, signal, idler. So you need conservation of energy, that's omega pump equal to the sum of omega 1, omega 2. And the propagation constants had to add up as well. That's conservation momentum. And without it, the interaction is very inefficient. And that was all in the 1958 paper by P.K. As a matter of fact, the great classic paper by Bloomberg, for which he got the Nobel Prize, that's a remark I wouldn't say in the United States, essentially took this paper and changed the appropriate constants into the optical language. But P.K. really deserves a major credit, which he never got. And Louisel and myself and Sigmund got involved in 1961. That's before the laser, essentially, or at the same time, this independent of the laser, in a quantum analysis of nonlinear interactions. And in what follows, I will give you the story of why we got into the quantum analysis and some of the consequences. A picture. Joe Domain is the fellow who first made the first parametric amplifier in optics. So, a lot of credit. Scientist, actually of Maltese origin, born in Canada at Bell Labs. Bell at the time really attracted the absolute. They went to the top universities and picked the students and said, "You come to work for us," and they got most of them. The only one we didn't get this way is Bill Bridges, who went. And so Joe Domain got a PhD in physics at Columbia. He did two things. He made the first parametric amplifier, and he also invented the technique of phase matching by birefringent. Phase matching is what you need to do to control the velocities of the three waves, pump, signal, and idler, in such a way that the efficiency of converting energy from the pump to the signal and idler is high. Remember that the original conversion efficiency was 10 to the minus 9 or so. If you do things correctly, and that's because phase conditions aren't satisfied to ensure continuous transfer of power in one direction. It's all a question of relative phases. And using the phase matching techniques, which I will not talk much about, but which you have one of the world's experts here in Adi Aryeh, so you can actually get conversion efficiencies approaching 100%, measured in terms of photons. So, and it was that turned it from a curiosity into a real practical field. More. So that's Joe Domain. Kleiman, those of you who may know, is the one who first figured out the mathematics of focusing with Gaussian beams, nonlinear conversion with Gaussian beams. A very, very good physical. And all of those people were working at Bell Labs. We were working together, same lab, next to each other, and other people who really, so it was a very exciting place to be in. Russians had a love affair for a long, long time with nonlinear mathematics and optics, so that extended into nonlinear optics. Most of this work was concentrated in Moscow State University. So this is not the Kremlin, that's Moscow State University in Moscow. And some of the key people there were Kakhlov, who died in a tragic climbing accident in the Pamir Plateau, and Achmanov. And this is Nico Blumbergen, who formulated essentially most of the theoretical tools that we use today in nonlinear optics and got the Nobel Prize for it some 20, 30 years ago. He was a Dutch, got his undergraduate degree in 1946 in Rotterdam. So he went to school during the war, Second World War, then became a young faculty member at Harvard. Okay, we now go back to the first meeting on quantum electronics. It takes place in 1960. That's before the invention of the laser, before the demonstration of the laser. And organized by Charles Towns, who later received the Nobel Prize for the invention of the laser, the idea of the laser. And the meeting takes place at Shawanga Lodge in the Catskills. Shawanga Lodge was one of the Borscht Belt hotels, lodges. How many of you know what the Borscht Belt is? A bunch of hotels in the Catskills, about 30, 40 miles north of New York City, were the poor immigrants, the Jewish immigrants who settled in New York City, in the slums of New York City, Lower East Side, got their families. Those who could afford it stayed in the lodges. Those who couldn't afford it stayed in little cabins. They came by the hundreds of thousands. So the whole region, probably as big as half of Israel, was full of those Jews speaking Yiddish. The big lodges had comedians performing every night in Yiddish. Many of them went on to become Milton Berle, Sid Caesar, the great comedians of the American theater, broke their teeth in Yiddish in the Catskills. So, the table of contents of the meeting, among other talks, is a part of interest to me. Here's a paper by Towns and Server on limits of electromagnetic amplification due to complementarity. Essentially, what's the noise figure, what's the noise or limiting sensitivity of a laser amplifier, which has not yet been demonstrated, maser amplifiers have, due to complementarity, meaning due to quantum mechanics, due to the fact that the number of photons and the phase are two conjugate variables, and you cannot measure both with absolute accuracy, uncertainty principle. But right next to that, there was another paper, Parametric Amplifiers and the Comparison with Masers by UF. So that's how, tell you more about them, that's how I got into the picture. Server and Towns, who wrote a paper on essentially the noise properties of the laser. Server was a field theoretician, and Towns was the great practical genius. So Server provided the mathematical tools. I think the work here is mostly Server. And the great thing about it, about the paper, he analyzed maser amplifiers, a question, where does noise come from? And he formulated a Hamiltonian. And a Hamiltonian essentially is a product of operators, field operators. B1 dagger creates an atom at the excited state. B2 creates it, annihilates, this creates one at the lower state, annihilates B2 at the upper state. So this operator essentially takes an atom and causes it to go from the upper state to the lower state, a transition. This is the field variable, A star. So this operator, by looking at it, if you work with field operators, immediately you can tell you create a transition and you generate a photon. Amplification. Okay? So you use this. The quantum state is a linear combinations of the states 1 and 2.
Why did you use B1 and B2 in the amplitudes for the atom?
Excuse me?
Those are amplitudes, not in the second line. They're amplitudes of the states 1 and 2.
B1.
In the top line, they're field operators that create and destroy states.
Those B1s are field operators. Those are the complex amplitude. So those are not operators, B1 and B2. We'll talk later. But there's probably a bad choice of choosing the B1 to be both an operator here and a coefficient, complex coefficient here. So without going into the details now, if you applied that Hamiltonian to the question here, you found out, and so I took the results of that analysis and translated it into the engineering term. So here's a laser amplifier. It's being pumped, of course, but I'm not showing that. And you come in with a signal SI, S input. S is the power. Okay? The gain of the amplifier is G. So being an amplifier, it amplifies the input signal by SI. But the output contains not only the gain times the input, which is what a classical amplifier would do, an exotherm. Exotherm has H bar omega B. B is the bandwidth. So as you know H bar, you know it's a quantum effect. And if the gain is 1, meaning if that's just a piece of perfect glass, this term disappears. This term is can be looked at two ways. Somebody like Serber will say, well, I got it. This reflects the uncertainty principle, the non-commutation of the operators involved there. But a completely equivalent way of looking at it, the amplifier amplifies as a classical amplifier, but being a laser, it has an upper level and a lower level. And spontaneous transitions go on at the same time as stimulated emission. Stimulated emission are responsible for the gain. Spontaneous transition, some of them work their way into the same solid angle and the same frequency as the signal and cannot be separated. And that's noise. Noise because this term is independent of the signal. So that's the noise. And that term is consistent with the uncertainty principle. If you use this amplifier to measure the number of quanta and the phase of a mode, you get this result. So Serber and company have shown that the laser amplifier is consistent with basic quantum mechanics, and therefore they called it an ideal amplifier. Amplifier cannot be any better. Not an amplifier, a coherent amplifier, an amplifier that preserves both phase and amplitude has to be. Okay. So much for the laser. Then Hafner got up, professor at Stanford, very, very good, but electrical engineer, so he didn't know quantum mechanics, and he described how his parametric amplifier works. And you recall parametric amplifier works on reactances. Here's a simple way. Imagine a capacitance. Capacitance is part of an oscillating circuit in a circuit. And there's a voltage, a time-varying oscillating voltage, so the charge on the plates varies with the optical frequency. There's a moment in time when the upper plate is positive, the lower one is negative. The two plates are attracted to each other. The charges attract. And then half a cycle later, positive on the bottom, negative on top, plates again attract each other. So when the plates, if the plates are at that moment in time, if you separate a plate, you are doing work against attraction, and that work goes into the oscillating field, and you repeat it half a cycle later. So if you look at the voltage on the condenser and the charges, it undergoes this jump for this model when you separate them. Okay? You can see right away here that the pumping rate here, the rate at which you are doing it must be exactly twice that of the frequency, because you're pulling apart both here and here. Okay? What's more, if the relative phase between the pulling and oscillation is not the one shown here, but out of phase, if you push them when it charges, then the other way around. Okay? You're taking energy away from the circuit. So, two things. This is the degenerate parametric amplifier, where the pump is twice the frequency, and we find out if it's degenerate, you need to have a phase relationship between the two. Correct phase to get amplification. If it's not, you get less gain or possibly loss. But those are not dissipative losses. Those are reactive. You're dealing only with capacitances here. That's the basis. That's what basically the story that Hugh Hafner gave us. Okay, a little bit about, not too important. I gave you the main story in words. In nonlinear optics, call it the Bloom-Again formulation, you start by, the basic physics starts with saying that in a material, at a given point at which you have fields, let's say at omega 3, pump, and omega 2, get two applied fields to the crystal. In the crystal, locally, you generate a polarization at the difference frequency, omega 3 minus omega 2. Okay? So that is the formulation of nonlinear optics. In microwaves, you say that if you apply to a nonlinear capacitance a voltage V3 oscillating at omega 3 and V2 oscillating at omega 2, you will generate a current at the difference frequency. The translation is 1-to-1. This is why the P. Ketian paper was so important. Nonlinear current in the microwave circuit plays the same role as nonlinear polarization in the optical case. The voltage-dependent capacitance of microwaves is equivalent to a field-dependent dielectric constant. Now, it's second-order optical nonlinearities. The optical nonlinearities which I use in circular harmonic generation as an example. They're very same. Okay. Hafner went on to derive the noise figure of his amplifier, and lo and behold, he said, in terms of noise figure, the noise figure of the laser, which we have described, had a noise figure of 2. That means the signal-to-noise ratio in the best case would be degraded by a factor of 2 between the input and output. Hafner said, mine has a ratio of 1. Therefore, the microwave amplifier is better than the laser. So that all takes place in Shawanga Lodge. I was in my first year at Bell Labs, and they graciously sent me to the meeting. So I heard of that, and even managed to ask a question that made it into the proceedings. Is it possible that the difference in the two is because Towns and Serber analyzed the maser using quantum mechanics, and Hafner used the classical analysis? So what one needs is a quantum analysis of the parametric amplifier, and they nodded their heads, and so I went back to Bell Labs, engaged the work of Louisel's help. He was in our group a very good physical mathematician. Later on, we added Sigmund. We found that he did some related work at Stanford, unknown to us, but it was close enough, so we included him. And the key immediately was to formulate a Hamiltonian. In quantum mechanics, you have a Hamiltonian, you find the eigenstates, the eigenvalues. If you disturb the Hamiltonian, then you can cause transitions between the eigenstates of the unperturbed Hamiltonian. So that's what we call the perturbation Hamiltonian. You needed to formulate it, and Hamiltonian essentially is energy. Okay? So if you have a dielectric constant, this nonlinear polarization that defines nonlinear optics, P dot E is the added energy to the field due to the nonlinearity, expressed in terms of the nonlinear coefficients, which are material characteristics. That's a tensor which describes like an extension to the first order nonlinearity of the concept of a dielectric constant. First, the next term, the Taylor expansion. So if you have fields EI, EJ, EK, then there is a change in the energy proportional to the product times the nonlinear coefficient. Integrated of the volume of a mode gives you the total change in the energy. Quantum mechanically, you change that into a Hamiltonian by essentially replacing every field which appears here by a difference between a creation and an annihilation operator. Okay? So the quantum mechanical operator, the interaction Hamiltonian, is a product of A creation minus A, pump, signal, idler. So assume that you have 3 optical fields. Okay? A is this involves the integral, and the concepts of phase matching is only the A. For the integral A to be large, you need to phase match, because that integrates the spatial part of the wave functions. Okay, since the pump is very large, we treat it classically. So we take a time-dependent variable, that's a pump, and the quantum mechanics now resides in those two. So this is the signal field, the idle field quantum mechanically. That's the key. So you see, inspiration comes from the paper by Serber, except we specialize it now to nonlinear optics. We don't have creation and annihilation operators on the atoms, because the atoms are involved but indirectly. They act as catalysts. The nonlinear interaction involves non-energy conserving, therefore very fast transitions within the atoms. But that's another topic. Well, if you now solve, given the interaction Hamiltonian, you can solve the equations for the operators. And we use here what's the Heisenberg In the Heisenberg picture, you solved the Schrödinger equation not for the wave function, but for the operators. It's a transformation to another frame. And in that context, it makes all the difference in the world. It's a more powerful. So we are in the interaction picture. And those are equations, two linear differential equation. Classically, you would get the identical equation. In the classical treatment, this would be the amplitude of the stock frequency, and this would be the amplitude of the idler. Okay? The two are just the two frequencies which together add to the pump frequency. There's no difference between them, but we give them names because in practice one of them is a signal input. Okay? Quantum mechanically, they are operators. Okay. And you solve those equations mathematically. I can take those equations, give them to a mathematician, and he doesn't need to know anything about quantum mechanics. He'll give me that as a solution. Okay. So that's the initial value of the operators. And you will see immediately from here that the two fields are completely intertwined, entangled. The basis of the entanglement of quantum mechanics of photons, which is used today in quantum information, is right this solution. You can see the signal at time t operator, which essentially has all the information about the optical field at omega s, involves both the initial values of signal and idler and vice versa. The two are mixed up, and one doesn't know. Okay.
Amnon, the AS in the exponent, should they be...
Excuse me?
Is there a typographic mistake here?
What?
AS dagger, AI dagger, AS, should they be on the level of the... they shouldn't be in the exponent, should they?
Let's talk about it later. You might be right, but I'm not quite sure. So rather than take the time. All right. So that's the solution of those equations, and those two equations are now used to essentially answer, in principle now, if you know the operators, and given the initial wave function t equals 0, you can answer any answerable question allowed by quantum mechanics. So the whole story is here. In engineering way of looking at this picture, billiard ball picture, is the following. You have three interacting waves. The whole picture involves three waves. Atoms are represented through the nonlinear coefficients. So they don't appear in the analysis here. So the basic process, primitive I don't mean no good, I mean the most basic primitive system, involves a transition in which there are three modes. You quantize the electromagnetic modes. Each mode becomes a harmonic oscillator. That's the pump harmonic oscillator. That's the h bar omega, the separation here, the frequency of the pump. And it interacts via the nonlinear coefficients with both the signal and the idler. And the basic transition, at t equals 0, you have a state where the pump is in this eigenstate. The signal is here, the idler is here. So they're all excited. The excitation quantum number are Np, Ns, and Ni, which could be 0. Now, this state could be here, in the ground state. We'll come back to that. That's the most general. And the interaction Hamiltonian, the perturbation, causes a transition, if you think of it in terms of Fermi's golden rule, in which the pump loses a quantum, one photon goes down, while simultaneously, at the same time, the signal mode gains a quantum, so go from ns to s plus 1, and the idler mode gains a quantum. If you apply Fermi's golden rule to this picture, Hamiltonian, to calculate transition rate, this is not a sophisticated picture because we are counting photons here. Phase is not lost. But it's enough to predict phenomena, as you'll see. You find out that the rate for this process is proportional to the number of initial quanta in the signal plus 1, idler plus 1, times the number of quanta in the pump. The plus 1 here and the plus 1 here are due to quantum mechanics. If you didn't have them, you did it classically, you won't have the 1. If you don't have the 1, you will lose a lot of the measured and new phenomena, as you will see. They come strictly for the fact that A dagger and A for a given mode are non-commuting operators. Okay, let's apply this idea to the noise. In a parametric amplifier, there's only one input. So let's say it's the signal input. So you start with NS0 photons in a mode, and the idler mode is unexcited initially. You cannot ignore it because the quantum mechanics involves both of them, or the classical, and the number of pump waves. Okay, so if this term isn't here, what is noise? Noise is an output at a given frequency, even if there's no input in an amplifier. So no input, put NS0 equal to 0, and you find out that the transition rate, involved the rate of generation of signal photons, is proportional to NP times 1 times 1. In other words, you can generate an output even with no input. Engineering definition of noise. And if you apply it a little further, you find out that, again, the output now is given by a gain times a single input plus G minus 1 times H bar omega SB. The very same expression for the laser. So by doing that, we have achieved what we set out to do, and that's to find out which amplifier was better. It was an engineering question, and we found out that they were identical. Both were ideal amplifiers. But the story didn't end there. There's a bonus there. Okay. You take a crystal and you only shine into it one frequency, omega 3. Okay. Remember, the rate is proportional to this, but those two, this time is 0 because we only have one frequency coming in, NP. And those aren't there. And therefore, this is the rate at which we generate photons at both the signal and the idler. So that means you take a crystal, you shine light into it, no threshold, no nothing. You get output photons at two frequencies which add together, because that's a conservation of energy, to the pump frequency. And, okay, and you have to, so that will be conservation of energy. The two fields which are generated obey this condition, conservation of photon energy and conservation of momentum. And this is the process, quantum mechanically. So you started from 0 for signal and idler, the ground state, and you generated photon. This effect, that prediction of generation of photons with no inputs, it's like fluorescence in linear optics, became known as spontaneous parametric fluorescence. It's a new physical phenomenon, unsuspected, predicted by simple quantum. As soon as you saw the Hamiltonian with the inertial creation operator, you know that that effect is there. If you ever worked with the field operators, which any student in first or second year quantum mechanics does, shows you the power. That's why actually, for the first time, I had a really gut level appreciation of the power of quantum mechanics. Till then, for me, it was a course which I needed to get an A or B+. It enables you to invent new phenomena. And lo and behold, okay, I've already shown this equation. And those two photons, of course, although they are spontaneous, they are entangled. They obey the same mathematics, which is expressed here, except with AS0 and AI0. Okay. Corresponding to no inputs. So you have a crystal, you get two photons coming out, and then what determines the two frequencies are phase matching. And that can be controlled by direction and temperature, as an example, or electric field. Spontaneous parametric fluorescence results in the emission of single pairs of correlated photons, signal and idler, which is the starting point for photon entanglement. And Harris, Oshman, and Bayer at Stanford, that's Steve Harris, very well known for the work, observed it back in 1967 and did experiment in lithium niobate, A and B. Those of you who knew Bayer and his very wonderful work he did later, were you his postdoc? That was his PhD thesis. Oshman decided to become a billionaire. I think he still is a billionaire. And they have observed it experimentally and also provided the basis. And they gave us credit for the prediction, although a little generous. That's the paper, Observation of Tunable Optical Parametric Fluorescence. Okay, those two photons are entangled. What does it mean? It means that if you, for instance, measure the arrival time of photon A, then you can predict when a second observer at B, which can be in opposite direction, will observe his photon. If you measure the frequency of photon A, you know the frequency of photon B, which will be measured by somebody else, because the sum of the two frequencies have to add up to the pump, which is null. It goes beyond that. If you play fancy games with the phase, by modulation and so on, there's a phase correlation which can contain information between the two of them. So the whole idea of quantum entanglement is the basis, is the starting point is what happens. It's those quantum operators.
Could you explain what the words energy entanglement and time entanglement mean? I know entanglement.
By energy entanglement, I actually took that slide from Steve Harris. It means that if you measure the photon energy, if there's a deviation, after all, the energy of a photon you'll measure, it's spontaneous parametric fluorescence, though there is a continuum of photons which can be emitted, because it's not, unless the parametric oscillator, it's not limited to one triplet of frequencies, pump, signal, idler. There's a continuum of frequencies here. So you can measure, determined by phase measure conditions. So in an experiment, you can measure the energy of a photon, measure the frequency, and it could be above the average or below the average. But once you've measured it, that energy deficiency, you have determined the energy deficiency of the idler. That's what Harris meant.
So I don't know if there's a direct relation between that and quantum mechanical entanglement.
Well, I've defined it. What I mean for that. I defined it as energy entanglement. Squeezing. Phenomenon, again, remember? I've shown you the classical parametric amplifier, the first one of the first slides, and showed you that in a degenerate parametric amplifier, you need to pump at twice the oscillation frequency in order to get gain, and you have to have the right phase relationship. And I've shown you the separation of the plates and the capacitance to give you a classical picture. So in a parametric amplifier, you can amplify or de-amplify, depending on a relative phase relationship between the frequency omega and the pump, which is exactly twice. That's why it's called degenerate. Okay, this slide is a little out of place. That shows the key people, UN, Shapiro, and so on, predicted squeezing. And in a moment, I'll define you. And one of the early, maybe the first observation, is by Wu, Kimball, Hall, and Wu, Kimball, a professor at Caltech. At that time, I think he was in Texas. Generation of squeeze states by parametric down conversion. Parametric down conversion here is essentially degenerate parametric amplification. Down conversion because you are annihilating photons at 2 omega and generating them at omega. Now, classically and ideally, electromagnetic field is a phasor. Complex plane, and that vector turns around at the optical frequency, optical rate. Quantum mechanically, one way of looking at it is this vector cannot be, the tip of this phasor cannot be specified exactly, but it's essentially, it terminates somewhere in that cloud of uncertainty, which is a circle. Simple way. It turns out that the area of this circle here is independent of the length of the vector in the proper normalization of variables here. So even if the field classically is unexcited, that means that classically the field is a dot at the origin. Quantum mechanically, the field vector can be terminated inside the circle, which is the same as this circle. This is the zero-point vibration of the electromagnetic field, demonstrated in this fashion. Okay. Now, if you take this field and operate on it with a parametric amplifier, okay, if the parametric amplifier is in phase, twice the frequency, but in phase relative to this long vector, you can amplify the component, let's say, along this direction, and de-amplify component in 90 degrees. And therefore, you can turn the circle into an ellipse. The area of the ellipse is the same as the area of the circle. That's kind of that's a classical description. The real treatment has to be done with the creation and the field formula to describe. The point is you can also do it on the zero-point vibration. You can take the unexcited zero-point noise, the zero state in the Glauber sense of coherent states of the quantum oscillator, and squeeze it. So now you have when you squeeze it, there's, so to speak, the uncertainty noise bar can be concentrated along one dimension at the expense of the other quadrature component. If you do so and you detect the number of photons, the fluctuations in the squeeze component, you should get less than shot noise. And that shows a thing measurement by Kimball and company of the shot noise of a detected laser beam which is being squeezed by second order degenerate parametric. So squeeze states. So essentially getting below shot noise by using nonlinear optics. Let's say this field had a major flowering, still active. And the last topic I want to mention on is a new field. At its beginning in Russia, people like Brzezinski and so on, in terms of quantum measurements, had to do measurements with minimum effect of the measurement on the experiment, back action. I will not go into it. It's a long history. Brzezinski is very well known. Might get a Nobel Prize one day. Hopefully with Kerry Valhalla, who did this, who is my student, ex-student, professor at Caltech. And what they basically do, it's a new field. Some of you may not have heard about it. Think about it as another parametric device. Remember, in a parametric device, you have two oscillating modes. There are two optical modes, and you pump. And you can feed energy into the two modes. That's the amplifier. Or if you put the modes inside the resonator, you pump and you get oscillation, monochromatic oscillation. That's the essence. Well, imagine where you simply replace one of the two modes by an acoustic vibration, acoustic mode. If there's coupling between the acoustic vibration and the optical fields, then you can write a Hamiltonian, which is identical to Hamiltonians I've shown you, except you replace the creation annihilation operators for the let's say idler mode, which you're now out of the picture, with acoustic creation annihilation operator. So you can tell almost the same story for this new generation. So it's a device in which we have replaced an optical field with an acoustic field. Here's an example. You have an optical wave, and the pressure here, radiation pressure, on this plate, there's a spring here, can change, it changes in this direction, and therefore pump, press like a harmonica, this harmonica, and set it into oscillation, what happens is that another wave is generated in the interaction, and it's the difference frequency between the pump wave and this wave coming out, which the oscillating intensity, the bit frequency, which acts as the force on the plate here. Okay. The key to that is, the key is to have very, very high Q optical oscillators and very, very high Q mechanical oscillator. And Brzezinski, who understood some of those things, did not have the technology. What happened at Kerry Vahala at Caltech invented this new generation of toroidal optical oscillator with Qs of up to 10 to the 10 or so. And if you those who work with Qs appreciate. It's an immense number. That means there's a tremendous amount of concentration of optical energy. You can feed in almost microwatts and see nonlinear effects. And it turns out that the mechanical properties of these very high Q resonators are also, so you have a combination of a very high Q optical mode, acoustic mode. Okay, so what does that predict? That predicts that you shine an optical wave at some threshold, it'll break into simultaneous oscillation at an optical wave, which is detected. Okay, the optical wave will deviate in frequency. It'll be somewhat below the frequency of the pump wave, and the difference frequency corresponds to the acoustic resonance frequency of this mode, and you will, at the same time, you will break into simultaneous oscillation. This will be the signal, outgoing wave, and the idler now is a mechanical ovation. So you have here a parametric oscillator and an acoustic laser. You've generated coherent sound. In Kerry's experiments, those dimensions are such that the oscillation is, forgot, somewhere about 5 gigahertz or so. And the frequency begins to be high enough so that the acoustic mode here may correspond to only a few number of, initially, of acoustic quanta here. Actually, recently it was done with no initial acoustic quanta. Now, the temperature was h bar over kT was large enough so that the effect that the acoustic oscillator acted quantum mechanically. Depends on the ratio of, okay? You can see another way that if you, by shifting the frequency a little bit, you can actually take energy out of the acoustic vibration, whatever it is, combine it with the oscillation here, and get frequency up conversion, and therefore cool the acoustic vibration. Depends on whether you are blue shifted or red shifted with the input frequency relative to the optical resonant frequency. So here's a new field actually being born. You can see it. You see it at Caltech. We have 3 or 4 experiments in different departments going on with this new emerging area, which is very exciting. So I think, let's see, try to show you, tell you a story. So it was semi-coherent. And to me, the interesting thing is how what turned out as a pure engineering question, what is the noise figure of an amplifier? You buy an amplifier, you want to know, led to quantum mechanics, to parametric fluorescence, a whole bunch of things. So the more I give to the students, it doesn't matter if you take any field, push it, you'll get to a boundary. If you're smart enough, and you'll probably be surprised. So thank you for your attention.
Okay, so thank you for this exciting talk. And are there any questions or comments?
I take it as a sign that my lecture was so clear that you understood everything.
Okay, so yes. Okay, so thank you very much.